Hello, my name is Aurora. I am a postdoctoral researcher at the University of Murcia, and in this video, I am presenting the work, A Combination of Multi and Univariate Anomaly Detection in Urban Irrigation Systems. It is for the third International Conference on Embedded and Distributed Systems. I will introduce and motivate the work, explain briefly some background and related work, talk about the methodology, use case, and experiments, and then I will conclude. Water scarcity is a global concern that requires a more intelligent way to manage the water network. There is a current need for new automated and intelligent decision support systems that employ data analytics to analyze in real time the anomalies and the problems that appear in water usage. Smart water management can lead to minimized consumption and also to reduce the water costs or billing, to reduce leakage, to a better management of pressure and to predict potential failures, among other uses. Smart water meters periodically collect measurements of water consumption. This opens up a wealth of opportunities for water providers when empowered with data mining techniques. This data, stored as a time series when considering each meter, can be also seen as a multivariate time series problem when considering full deployments. Anomaly detection serves for different purposes that go from general water quality analysis to more specific applications, such as measuring the changes in consumption to reveal leaks, finding device and method failures, detect illegal water use, warning situation, peak water usage patterns, etc. We encountered that the problem that normally anomalies are rarely annotated, and therefore we're in need of a methodology that is based on unsupervised methods that looks for patterns. Outliers and anomalies are terms that are largely used in an interchangeable way. Outlier detection techniques can be classified according to the kind of input data, univariate and multivariate, and also according to the type of outlier, point-wise, point outlier, and pattern-wise, or subsequent outliers. So an univariate time series X is defined as an ordered set of k-dimensional vectors, each of which is recorded at a specific time t, and consists, it can be seen as a series like this, x1, x2, x3. A multivariate time series X is defined as an ordered set of k-dimensional vectors, each of which is recorded at a specific time, again t, and consists of k real valued observations. We can think of it as a several time series, where here there is one time series of the previous kind, then the next component is a second time series of this kind, and so on. A point outlier xt is an observation that behaves differently than what is expected by a certain threshold, delta, let's say, where xt is the real value, x hat is the expected value, and it is one is different from another, a certain threshold. And finally, pattern-wise outliers are a set of consecutive points in time whose joint behavior is unusual. It could be basic shapelet, like a new form in the shape, seasonality changes, and some other trend alterations. As for related work, there are works that have been used to find water usage anomalies in household using clustering mechanisms such as DB-scan and CAMINS. Also, the punctual anomalous water consumption has been found using STL decomposition and seasonal hybrid STL test, manually spikes, jumps, drifts, or layers. And there are works comparing multivariate and multivariate supervised methods. So the existing approaches, normally they choose one strategy or the other, or compare two of them but they don't take advantage of the complex and dynamic behavior present in water systems. They are using just one approach and not trying to use hybrids, which is what we are going to do. The water consumption of parks. Let me introduce you to the methodology first, the data set that we have used. The water consumption of parks in the city of Murcia, Spain, is provided by the municipal water and sanitation company called EMUASA. The company manages the water supply for approximately 400,000 inhabitants, and it is also responsible for managing the water supply to industries, stores, leisure centers, and parks. In our use case, we're going to focus on the parks. Each park's water meter indicates the water volume that passes through them to a remote reading system that stores the data in a server. The water meter measurements are present in different granularities, minutes, hours, days, and even weekly sometimes. Most water meters have data between September 2017 and July 2021, therefore almost 3 years. And the data presents some problems or challenges even before starting to analyze it, that we needed to fix through preprocessing. We found negative water consumption due to water return. We found sometimes when the water meter is changed, there's a sudden change on the number return. That doesn't make sense when subtracting the measurements, because the consumption is the smart meter is just measuring the consumption like on an accumulated way, and we need to subtract every 2 measurements. And when there's a change of a smart meter, there's a problem. And then we have different starting and ending days. After the cleaning, data was homogeneously aggregated every 15 minutes, and we count on 283 time series. In that sense, the data that we count on is huge in volume. As I said, we have 283 series, and in dimension, the data every 15 minutes for almost 3 years. Therefore, univariate methods are not feasible because they consume a lot of time. In that sense, we use a multivariate technique that will tell us for a group of time series where there has been an anomaly. The methodology that we have come up with consists of, first of all, cluster the parks according to the water consumption in order to have similar groups. Then, for each of these groups, apply multivariate anomaly detection to identify general anomalies. And then we apply univariate anomaly detection for each series in a range close to the previously detected anomalous dates for the cluster. In that way, we reduce a lot the number of points that is tested. For the clustering, we've used hierarchical clustering, more concretely top-down approach, where the beginning observations belong to the same cluster and splits are performed recursively according to the distance as one moves down the hierarchy. The distances we have used are Euclidean, Frechet, DT warp, and correlation based. Here you can find the formulas. I will not explain the measurement, the metrics further, because I think they're quite general knowledge. We selected manually through visual inspection 3 clusters, also according to the distribution that we saw in the metrics. On the one hand, both Euclidean metric and the Frechet method presented similar behavior, which means a few of the series were grouped in smaller clusters, and many of them were grouped in a greater one. This was a similar behavior between Euclidean and Frechet. On the other hand, the dynamic time warping and correlation-based metrics provided a more balanced distribution across the clusters, and this is something that's more interesting for us, for our problem, because we want to have a few series in order to apply our multivariate algorithm to each of these groups. Now, for the multivariate anomaly detection, we have used the vector autoregressive model, VAR, var relates current observations of a variable with past observations of itself and past observations of other variables in the system. Var models differ from univariate autoregressive models because they allow feedback to occur between the variables in the model. You can see in the screen the formula that does not include exogenous variables, exogenous. We just used for the width sub t. So when we want to predict a certain value, we use some width lag of itself. Then alpha is a k-vector of constants that is can be interpreted as the intercept of the model. Phi so y is a time invariant k times k matrix, and we have also an error time vector. So in order to have an example of a process of a vector autoregression of one lag, if we have 3 time series, let's say yt 1, 2, and 3, then the formula is spread as you can see in the screen. And now it's a little bit clearer. In order to use the var for anomaly detection, we first perform the predictions using var and compute the square error where these are the real values, these are the predictions, and we compute it as you can see. Then a threshold is defined where SD is standard deviation. If the square error is greater than the threshold, we find an anomaly. The results of the var detection differ a lot between groups. This figure shows the results of the groups generated with the correlation distance. We have selected some clusters from the picture in order to show you 2 different behaviors. There are some times that the algorithm finds a great number of anomalies, so many. This is for clusters 3 and 4. And other times they just find a few because there is maybe one series that is clearly having a different behavior and all the rest are more or less similar. So we encounter these 2 types of scenarios. Now, for each of the clusters, we will select the date in which the anomaly was found, and for all series, we will use an univariate method around a range. So you see that in this case, we have gotten rid of a lot of trials. Here is less convenient, right? But still, it is quite a lot. So to analyze the univariate series, we follow the NARIMA framework that can identify 5 different types of outliers: additive, level shifts, temporary change, innovative outliers, and seasonal level shift. We will not go into detail, but if you were interested, here you can find the reference of what do all these ones mean. For us, we will consider just 5 of them as an outlier. And if ZT is an ARIMA model, then it is assumed that our series YT, which contains M outliers, can be described as you see in the screen. This is an indicator with value 1 when there is an outlier in TJ. And this is the outlier itself, which follows a certain formula depending on the kind of outlier that it is, and WJ is its width. So, as I said, the multivariate anomalies have associated a date with them, and there are a few dates for every cluster that are going to be further studied with anomaly detection for univariate, with univariate methods. We have selected a range between 30 days before and 5 days later for the detected anomaly using var, and then applied the ARIMA framework. In the figure, we see the real-time series without layers that is in gray, okay? This is the real one, because in blue you have the corrected one. The outliers, the univariate outliers, are portrayed with red points, and this red line, vertical line, is the anomaly detected with the multivariate method. So in the first row, the univariate and multivariate anomalies are very close together. So this is very successful because we have identified an anomaly an univariate anomaly thanks to the multivariate one. In the second row, although there are two univariate anomalies, the first one is not detected by the multivariate algorithm, but the second one is. And in the third row, whereas the first series shows a coincidence between the anomalies, in the second row, in the second column, sorry, is not the case. So although the algorithms find anomalies, many of these may be false positives, so an expert's view. And in that sense, an external validator will be needed to further evaluate the performance of our methodology. So to conclude, our work is about the development of a methodology for unsupervised anomaly detection in IoT deployments, which have several sensors spread through some geographical area. We capture first the general knowledge that is present in several series through the multivariate analysis, and then search for specific anomalies using univariate analysis, saving a lot of time. Our method is applied for searching anomalies in the irrigation of urban parks, but it is general enough for its use in greater agricultural setups. Thank you very much for your attention. We'll be happy to address your questions. Here you have my email, and this presentation will be uploaded in my GitHub account. Thank you.